I normally avoid trying to do hard calculation because it kills my brain. But this week I did something really hard.
Whoa.
So in a year, there's 52 weeks. We do one podcast every 2 weeks. And this is the episode number 26.
Oh my gosh, have we officially been going for 6 months?
No, it's a year.
No, but... Oh, I'm so dumb. See, I'm not great at calculations either.
So welcome to the 26th episode of Randomly Type.
Hi, I can't math.
Hi, I'm JS.
So JS, you program computers with languages?
I try. Well, people pay me to do it, but, you know.
So you must use one of the assorted languages, which enable you to program the computer.
Yes, I do, Lance.
Can you tell me about them? Could you just name a few?
Okay, normally I would say I do Ruby, JavaScript, Rust. That would be my normal set.
How would you qualify them? What's a differentiating factor between them?
They don't run all as fast. I would say Ruby and JavaScript are slower than Rust. Rust is statically typed.
Aha!
Okay, that's where you're going.
Yes. So they're typed, right?
Well, they're all typed.
So can you please elaborate how they're all typed? I was going to go there next. How are they typed?
Like, so for example, in Ruby, you have strings, you have ints, so they have those types. But you don't know at compile time here with air quotes, because there's no really compile time in Ruby or JavaScript. But at compile time, you don't know the types. You need to run the code to know what's the types.
So those are two different things, right? They're two different dimensions of typing.
Right.
Could you elaborate on those? Like, do they have names? Or?
Yeah, so like for Rust, you have your static types and your dynamic types. So the static types is while you write the code, you know that variable will be an int. And at runtime, well, it will match, most likely, except if you have like generics or things like that.
And it also has like types at runtime in that I guess Rust is like knows for the most part what it's doing, but if you tried to do an illegal cast from an integer to a float at runtime, it might blow up.
Right.
So it does still have runtime types as well.
Sure.
What I was trying to get at is there's like strong versus weak and static versus dynamic typing that you'll hear a lot. And especially as I was starting, I was very confused between the difference between strong and static.
Yeah, I'm not sure to understand the difference between strong and weak.
So the only weakly typed system I know is C. So in C, you can convert a bunch of bytes into a data structure willy-nilly, as you like. And as long as the memory representation of this thing is the same, it'll run. There's no like...
Can't you do it in any other languages like C++, Rust? And
No, well, you can't do that because it will fail. Like the runtime will usually catch this and or panic, right? Whereas if you just point at a random place in memory in C and you say it's an int, it will believe you, and then it'll try to run it and possibly run into undefined behavior.
I'm pretty sure you can do this in C++ with like... because I know there's always, well, often like void pointer, you need to cast them to understand what it does.
Maybe C++ as well. I'm not too familiar with C++, but definitely in C. Yeah, you could just like void pointer into nothingness and say that it's an int or convert between types. And as long as like the memory representation of this thing is compatible, then it works. In languages like Ruby or Python, if you say something is a string, it is a string, and there's explicit ways to cast it at runtime.
But you can transform them from one to the other.
Right, exactly. So C is weakly typed in that there's not really there's no concept of types at runtime in that.
Okay.
But like the Python or Ruby VMs, like they know what a string is at runtime and how it can be operated upon and things like that. So that makes them strong. But then there's also static and dynamic. So you mentioned it a bit before that Rust is static and strong. Static is mostly that it is, you kind of declare your types up front, and that's not always the case with type inference, but generally you declare your types up front, and without even running the code, with no concept of the runtime or how it'll behave while you run it, it's able to assign logic to the different bits of code based on these types.
Right. And it makes sure that it works together.
Right. And with Ruby and JavaScript, all bets are, they don't have this, so it's dynamic for the most part. And all bets are off. You have to run the program with a specific set of inputs to lead to the point where you want to assert some certain thing and then see if it blows up or not.
How would you categorize TypeScript?
So that's like a gradual type system. Yeah. So, I mean, it does have a type system on top of it, which can attempt to make assertions about it. So, I mean, I would say it's probably static. It's just that your types can be really weakly defined, right? It just might not be able to make the right inferences or make much use of the types that you ascribe to your things.
Static, but with some limitation.
Well, I would say it's probably static, but you're able to give it virtually no input and it'll give you no guarantees afterwards, right?
Right.
Yeah, a type system is like a lot of these runtimes that are statically typed come with a type system. And this is basically just a program, right? It looks at your source files and without actually running the code, it can, from the types, determine whether all representations of your program could work, right? Could run kind of in advance before running it, know that these states are legal, or if you're doing something wrong that it won't be able to run when it does run.
Mm-hmm. So you'll avoid errors of the type of null plus int.
So that's a very common one. Null checks, right? That's a very common one.
Yeah, so you won't need to check it at runtime because you know that the compiler would prevent you from doing this.
Right. So Rust is one. There's a lot of statically typed languages. I mean, like Java is one, C++ is one, Scala is one. I'd say like the most sophisticated ones are probably Rust and Haskell are the ones with like the most academic backing and do the most sophisticated transformations. And
I'm sure there's some that are 10 times worse, but they're not widely used.
Widely used, yeah. So now we know what static typing is. We know what a type system does. Do you think they're useful?
It's an interesting question. I would say it depends. I really like static types when I do a project which is more than like 10 lines of code, because it makes sure that I'll avoid some errors that I would normally do with dynamic languages. So for like quick scripting for my OS, I would use like Ruby, Python, Bash, whatever. But for any real project, I would like something that's typed.
Right. It's very comprehensive, right? So you could have a 10 million line code base, and it can usually give you some sort of result, right? Putting this code base through your type system can give you errors or not give you errors. So we actually touched upon this, basically, reporting errors a while ago in the Gödel's incompleteness theorems podcast. So if you haven't listened to that, it's tangentially related, so it could be interesting. But we'll go over soundness and completeness again, because I think those are really important things to consider when you're talking about type systems and like how and why they work. Do you remember what those are? Like those terms are?
Oh boy. All right.
I haven't prepared here. If there's a safety net.
Okay. What was the two words?
Soundness and completeness as they relate to type systems.
Okay. So I think completeness means that you can represent anything with it. So something that's complete, you can represent anything. Soundness, I think, is that it prevents you from doing illegal things or things that doesn't make sense.
That's actually a very good summary. That was excellent. So what I wrote down here is that for soundness, what soundness is if the type system says it's valid, then it will be valid at runtime. So it means there's no illegal states in your program. Practically speaking, this is very hard to achieve, but also likewise with completeness is very hard to achieve. What completeness is if the type system says it's invalid, then the runtime is not valid. So practically speaking, most type systems are incomplete and also unsound, but incomplete because they often prevent you from writing valid programs by saying that there are type errors. It doesn't encapsulate the full set of rules. And so in order to accommodate for that, it'll not be aware of some at the type in advance, but when in fact they're actually true. Like if you inspect it and actually run it, it'll always be certain, always be true. Mm-hmm. So ideally, a type system is both perfectly sound and valid. But if you go listen to the previous episode, you'll learn that we can prove that there's some systems that can never be 100% complete. So you can never count on a thing being 100% complete all the time. Cool. Now with this background, we can talk about variance in types. This is where things get I found it very hard to grok this until I watched a Strange Loop conference talk where Ben Weissman talked about a good mental model for reasoning about variance and it being applied to type systems. We can link it in the show notes. A lot of the examples below are going to be the same and or similar. When I say variance in type systems, what mental images does that evoke for you? The frustration?
Yes,
banging
pain.
your head on the table?
Yeah, totally. Every time I need to go read the Wikipedia page about variance, I know I'm in deep trouble.
Yes, and it's happened to me more than once too, where I wasn't sure if like the type system was wrong or if what I'm doing is wrong.
I would say 99% of the time you are wrong.
Yeah, that's true. Almost all the time, yes. But it's I had to write these things down because I never remember them. I find them very difficult to remember, actually. Just the terms themselves are very mathy. So it's nice that we can put this into stone by talking about it in a podcast so that we could always listen to it again later.
Which is definitely faster than going on the Wikipedia page.
I would hope more enjoyable anyway. If you had to guess what variance in type systems meant.
Oh boy. I know what it is, but I have no idea how to describe it.
Cool. So let's imagine a type system where everything was concrete. If you gave it a type, it is always that type. There's no hierarchy of types. How would that system behave?
It would be frustrating.
So that one is actually simple. Like,
right.
If a thing is a type and it is a singular type, it's always concrete, it never changes. That level of abstraction is very simple in that if you say this function accepts this type as this argument, it will always only ever be that type, and there's no shenanigans, right?
So this means that you wouldn't have a type like number, which could be an int or a float.
Exactly. So those things would be disallowed. You would have to only manage one and convert between them all the time, which in a lot of situations is frustrating, right? Oftentimes you want to represent groups of behaviors, or you want to represent inheritance, or exactly things like that, numbers, right? I don't care what number this is, I just need to treat it as a number. It also sort of models the way we think, right? We think in hierarchies. We're in a room, which is in a building, and I guess like a square is a shape and a circle is also a shape. So what is a shape, right? And how can we treat that in our programs? So variance describes the rules of subtyping, the validity of subtyping in type systems. And subtyping deals with very functional programming sounding term called higher-kinded types.
Oh boy.
So these are things like arrays, maps, functions. So it's like, how do I represent this complex hierarchy in things which kind of like nest them?
Right, where it contains the other types.
Right. And so this, just the description itself is like not pleasant. So actually going through the examples can also be pretty difficult. I figured what we could do first is explain all the different types of variance, whether they make sense in the real world or not. We can talk about afterwards, but just so we know like what all the terms are and what they mean. So it's also important to keep in mind that variance only makes sense when you're talking about subtyping in hierarchies and as it relates to things which accept those subtypes or deal with them in some way, like generic things which deal with them. Cool. Are you ready for an adventure?
Oh boy, yes.
Whew. All right, we haven't even started and I'm already overwhelmed.
Oh boy.
So there are 4 types of variance. There's covariance, contravariance, invariance, and bivariance.
Oh boy, I don't know about the last one.
Let's pretend we're dealing with arrays. So arrays are a great example of them having variance rules because it's a container, they hold other types, and that other type might be one in a hierarchy. So it's a good example for trying to reason about it, and everybody knows what an array is, right? Let's use the example that a square is a subtype of shape, and a circle is a subtype of shape. So shape is the parent type.
So here we're doing inheritance.
Yes. So if arrays were covariant, that means that an array of squares is a subtype of an array of shapes.
So if your function can accept an array of shapes, it can accept an array of squares.
Yes. And this is, I think, intuitively, humans think this way.
Right.
And that like a square is a smaller set of things than a shape. So an array of squares is a smaller set of things than an array of shapes.
Right.
We tend to think in that way, and that's covariance. Contravariance is the opposite, actually. So it's a square is a subtype of a shape. So an array of shapes is a subtype of an array of squares.
This one is weird.
So yeah, intuitively it's very weird. You're like, why would I ever use this, right?
And what if you have circles? So this means that your array of shapes is a child of both?
So that's why like these rules don't necessarily make sense for arrays, but this is sort of how they're defined, right? And very shortly we're going to go through the different higher kind of types and try to see like which one of these rules actually makes sense. Invariance is one where a square is subtype of a shape, but an array of squares is completely unrelated to an array of shapes. There's no way of converting between them. There's no hierarchy when you put them into a container like an array. And bivariance is both contravariant and covariant. So it just doesn't matter. Like an array is both a supertype and a subtype.
Okay.
Yeah, so that one we actually don't see anywhere. It's a bit strange.
Is it actually usable or no?
I haven't found a use case for them.
Okay.
It's more just like, well, there's invariance, so there's also bivariance, right? Just like logically speaking, there's the 4 combinations. So generally speaking, arrays are usually invariant. What that means is that if you give something an array of squares and you give it an array of shapes, the type system usually says like, nah, this is not going to fly. I do not recognize these things as related in any way. So that's the case for arrays, but that's not always true. And now we're going to get into like the why. Like these rules seem very arbitrary. We can get into the why, like why it makes sense to treat certain things. So what it actually has to do with, like these complicated rules, has to do whether you're producing or providing a value versus referencing or reading from or consuming a value. And that's actually what kind of how we ascribe these different types of variance to different types of containers and higher kind of types. So let's imagine the example where there's entertainment, which is the highest level type, and music is a form of entertainment, and metal is a form of music.
Right.
Let's go with that example. This example is from the video. Please check it. I want to give all attribution to Ben Weissman. This was good stuff and was the moment which made it click for me. Let's pretend we have a producer of all of these hierarchies of types. So you have a producer of entertainment, you have a producer of music, and a producer of metal, right? Those are different kinds of jobs, right? Yeah, it's like the most vague to the most specific, which is corresponding to the types. So now if you are a consumer in need of a producer of one of those, if you want to consume entertainment and you receive a producer of entertainment, you're cool. Like we know that this is fine, right? This is kind of what we expect. Nothing can go wrong. Similarly, if you're like, okay, I want to consume some entertainment, you can also receive a producer of music and you're like, oh, this is also great. Like this works in my case. Same thing with a producer of metal. This also works. However, if all you want to consume is metal and you received a producer of entertainment, you can't necessarily guarantee that in every case you'll get what you expected.
Right.
So the function return types are considered as producers.
Which makes sense.
Which makes sense, right? Like you're returning a type, you're giving it to someone else, you're creating this thing, which within your system can be consumed by other things. So by all this logic, we know that function return types are producers. So they're covariant. That means that they behave covariantly because if you're consuming this, like if you're calling this function and you're getting...
So if you want to listen to metal, you don't want someone that produces other type of music. So you don't want a higher type.
Yes. And if you get that higher type, you can't guarantee that that's what you want, right? And which is the type system's job, is to guarantee that this is sound. So that's why producers are covariant.
Wait, no.
Yes.
Covariant?
Yes, covariant. Function return types are producing values. So if you're consuming them, they can be treated covariantly. So if you're expecting to consume a shape and you get back a square, that's fine. If you're expecting to consume a shape and you get back a shape, that's fine. But if you're expecting to consume a square and you get back a shape, that is not fine. And that makes sense because we defined function return types as respecting the hierarchy of the original types, which is covariance.
And does this work with arrays? So like returning an array of shapes.
We'll get there.
Okay.
So next, let's talk about consumers and function arguments. It's kind of the opposite scenario, right? When you're inside a function and you're being given a value, you are then consuming that value. So let's look at one more hierarchy. You have energy sources, which is the super type, a subtype of which is vegetables, a subtype of which is bamboo.
Sure.
So now let's look at the consumer of all of those types. So a consumer of energy sources is greater than a consumer of vegetables, which is greater than a consumer of bamboo from the existing hierarchy. But if you want to produce energy sources, you can retrieve that value or consume a value of energy sources, and that would be fine.
So this is the return value.
Yes, but from your perspective, as your role is to produce energy sources, you need to consume energy sources to be able to fulfill that requirement.
Right.
But if you wanted to produce energy sources and all you can consume is vegetables, that doesn't work because you won't be able to necessarily fulfill your contract of producing energy sources. So like, let's say you wanted to produce vegetables, you can ask a consumer of energy sources or a consumer of vegetables, and that would be fine. So function argument types behave contravariantly. That's because they're seen as consumers, right? Like when you receive the argument, you're consuming it. So they're contravariant in their argument. And we can go back to the original example, which is that your argument type is a square, but you're consuming from a shape, you may not get the right value that you're expecting.
Yeah, because the producer could have given you a circle.
Precisely. So that's where contravariance comes in that it's sort of the relationship of hierarchies is flipped. Whew. Oh my gosh. I hope you had your notebook ready, listener. So
editing this episode will be so fun.
Yeah. Note to self. Yeah. So arrays are complicated and hash maps are complicated. It's usually most easy to treat them as invariant because they can be producers and consumers, right? In a single function, you could read from and write to an array. And so in most cases, unless you have a super sophisticated type system, you just want to be more sound, but less complete. And that some programs might not be writable if you assume that arrays are always invariant, but you can be sure that it'll always work.
Right.
However, in languages like Rust, mutability is a first-class citizen. So you could say an array is immutable and you can only read from what's inside it. And if you do so, then that array can only be a producer of values. It cannot consume values from your function.
So now you don't need invariance here.
Exactly. So if you have an immutable array in Rust, it's treated covariantly. But if you have a mutable array in Rust, it's treated invariantly.
Oh, interesting. And can you get only mutable? Like that you cannot read from it? Like a stream, I guess?
I was wondering the same thing. So that you could like make an array contravariant because you would only be able to write to it and it would be consuming your produced values. But I've never seen that. Like
I feel like a stream would be that. So you can write or read from it, but you cannot ever do like the other thing.
So I agree with you, actually. I think that makes sense to me in that you would have some kind of data structure which is write only, but not readable. And in that case, you would expect that it could be treated contravariantly.
Right.
But practically speaking, in like the general programming languages that we have, like we assume that if you can write to it, then you can also read what's inside. So I've never seen like a practical example, but theoretically.
Okay. I have one I used like some weeks ago, channels in Rust. Because like since you split like both part of the channel, you only get a half that you can read and half you can receive from.
Right. But I'm not aware of Rust, the type system, declaring this as write only and that you cannot read from it. I mean, maybe like that could be an extra like improvement going forward.
Right, I see what you're saying.
But like if you declare something as mutable, you're allowed to read it.
Right.
We would need like an extra type to say mutable, but I am unable to have exclusive access to this, right? I only want to write to it.
So you don't get contravariance from that.
Right, you do not, exactly. But theoretically, you could. Right. I've just never seen it practically done. all of these are based on substitutability as a constant. So if you say that I'm expecting a square here and you're given a shape, all you need to do to know if this makes sense is whether you can substitute all concrete types of a shape into that scenario. And in that one scenario I just described, that's not true, because if you're expecting only squares but you're given shapes, then you could be given a circle and that would violate your type system constraint.
Mm-hmm.
So if ever in doubt, re-listen to the episode or just manually try to substitute all concrete types of a supertype and see if it works as you expect in that scenario. That's all I had for today. I'm sorry for breaking your minds. Very difficult to reason about, but if you really break the problem down and just substitute everywhere you can kind of get a feel for whether this data structure is a producer, a consumer, and then whether you can substitute all values of a supertype or just specific ones. And then for your specific scenario, know how this works. Did you have any questions, JS?
Probably, but I need to think about it first. So I'll send them by email.
It's totally fine to forget. I always have trouble with the names. Like 1 week from now, I'll be like, what does covariant mean again? I need a mnemonic to remember what it means.
Do you have one?
No, I don't.
Oh, shit.
So I always have to, I have trouble referring to the concepts, if you know what I mean. Like argument position is supposed to be contravariant.
I was sure it was the inverse. So
no, function. Yeah, so you see, exactly. The words are too similar. We should replace contravariant with flu variant or something like that, and you would get
our argument variance.
Or like
return value.
Or like consumer variance, right?
That's good.
Versus producer variance. You heard it here first, folks.
I'm sure there's someone from your university that's screaming right now.
Absolutely. Yeah, I mean, as with most things, we're only discovering these things as we go and then talking to each other in a small dark blue and orange room with
way too much echo.
Yeah, it's way too much echo, way too much deco. And we just have a bunch of you all listening. So
by bunch, he meant 10.
Yeah. The ones we force to listen to us, and that's about it.
Hi, Mom.
All right. Thank you so much, Jess. Talk to you next time.
See you next time.
Bye. This podcast is both free and free, as it's distributed under the Creative Commons.
You can contact us and find show notes on our website, randomlytyped.com.
The intro music is by Vansky.
Thank you, Vansky.
And thank you, listener, for indulging us.